So Dhruti is saying, could you add me to the conversation? So how do I just need to send her the link, right? Pitu? Come on.
Sir, on the top of the chat, there's invite more people. You have to click on that and go to the content.
Yeah, yeah, but see, acha, Ritu is on. Okay, Dhruti is on my call. It seems okay, so I can add her there. Let me see. Add more people. Dhruti. Yes, I can add Dhruti now. And I have added her. Okay, now who else? Who else is remaining quickly? Shraddha, is all okay with you now? Anirudh, have you joined?
Yes, sir.
Excellent. Shraddha, can you please confirm? Shraddha is not there yet. Okay. So, since we are already live on the YouTube channel as well, so we'll begin the session, and I think people can join in as, as deemed fit from time to time. Yeah. So, if guys, if you notice any messages on the WhatsApp channel or on the chats here or at Google Hangout, please tell me if I should respond or act on it because I'll not be able to get in, right? But I'm just beginning the session now. Yeah, everyone who seems to want to join are there on the call now. I'm going to share my screen on both the platforms. So I'm sharing my screen on Skype to begin with. Let me see. Let me know if all of you are able to see my screen. Uh, Anirudh, are you able to see my screen? Ritu, are you able to see my screen? Dhruti, is my screen visible? Okay. Now, guys, I request all of you to mute all the others who are there on the call. They could mute yourself so that, yeah, if you could please mute. Shraddha, Shraddha, there's something at your end. Rest everything seems okay. Uh, yeah, Shraddha, you have to mute yourself. I think it's Shraddha's background noise that I'm hearing. Okay. Mute. Okay, guys, so let's begin. Okay. Anyone who's not getting any info or not able to hear me, just feel free to stop me at any point of time. Okay. Now, can someone just tell Shraddha to really mute herself? Because it's only Shraddha whose mic is on now. Rest everyone seems to be okay. Yeah. Okay. Now, so in the last class, we had seen how basically atom and their structures, react with each other. Today, what I wanted to touch base upon is on carbon-based compounds, which is also the core fundamental of organic chemistry. And just last class, if you have seen, uh, Shraddha says she's muted, but I don't see her to be muted. Uh, Let me see if she's muted or not. No, she's not. So I'm going to mute her myself. Okay. Yeah, she's muted now. Okay. Somehow I'm hearing the background noise any which way. Uh, okay. Okay. So let's begin. Uh, yeah. So I was saying that the study of carbonized compounds has a very special place in entire chemistry. Now, we have seen this data point time and again that more than 15 lakh compounds were just registered last year, right? Now, where do all these compounds come from? Nature some compounds are found in nature, some compounds are synthesized. The idea is that whether it is found in nature or synthesized, if it is useful for us, then we go through the process of registration. Okay. Now, if 15 lakh compounds themselves were registered, it means much more were actually, uh, uh, you know, uh, oh, one second. Okay. Yes. Now, if 15 lakh compounds were just registered, about 1.5 million, that means much more were actually found out or assimilated or synthesized. Okay. Now, let's look at the key factors of this entire chemistry. This is a very new chapter for us, and uh, you know, um, uh, so I would like either Anirudh or Ritu, one of you, because I think you guys have a good reception to respond to the questions so that I understand that it's going in the good flow. Anirudh, are you able to hear me? Ritu, are you able to hear me? Okay. So, have you seen at any questions from previous year in terms of the Nivedita Anand? I think this is Shraddha again. Hello. Shraddha. Now you just go to the YouTube channel and join there. Because only you are not able to join. The rest all have been. This has been a Skype problem. So I've posted the YouTube link. Just join there. Don't worry. Yeah, just go to YouTube and watch there. Hmm? Yeah, yeah, yeah. Uh, yeah. So what happens is that
Did you said anything?
Shraddha, I'm just disconnecting the call because I'm on the recording already. Yeah, yeah. Sorry. Ritu, we have not looked at carbonated compounds at all, right? Did we do catenation in the previous class?
So we did that. That's why we did expanded form, stick form, and condensed form.
Very good. So today we are going to look beyond all of those forms. And the first thing that we need to understand, so we had also seen classification in the last class. Do you remember? Functional groups is what we had stopped at. Functional groups is what we were discussing. Now, see, majorly when we say hydrocarbons would have only carbons and hydrogens in them to begin with. Okay. Now, when we keep on adding multiple other compounds, we find that these compounds are slightly foreign to what our basic fundamental compounds would look like, right? Let's take an example. So I have a carbon compound. Anirudh, are you able to hear me? Anirudh? Anirudh is not able to hear me. Okay. Dhruti, are you there? Okay. Not sure where these guys are. Okay. So, see, let's see that, for example, if we take a compound which has 4 carbon atoms and all the hydrogens around them, I'm going to replace each one of them by a different group. Okay. So what I do is I take out a hydrogen and I'm going to put, let's say, OH in it. Let's put with a different color. So let's say an OH. Now what I'm going to do is I'm going to take another hydrogen. So I just remove this hydrogen and I add a group called as O and carbon, OCH3. Okay. Now I take up one more hydrogen and I add another group which could be a C double bond O OH. Okay. So these are very foreign to the normal hydrocarbon chain where there is not just hydrogen and carbon, but there are oxygens in it, and these oxygens are in different forms. So these are called as functional groups. In the last class, we saw that. What is a functional group? A functional group is something which is foreign to a hydrocarbon. So it is a group of atom or atoms which is foreign to a hydrocarbon. But one of the most important things is they decide the chemical properties. Okay, they decide the chemical properties of that particular hydrocarbon. So no matter how long the chain is, let's say we have 20 carbon atoms which are just hydrocarbons one after the other. Like if we have to do the stick model, it would be something like this, right? So how many carbon atoms are this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 carbon atoms in this. But at the end, if I just write an OH, it will so happen that this OH is what is going to dominate the chemical reactions in this entire carbon chain. carbon chain. If there is any other chemical reaction happening at the other end, that will work, but at the same point of time, this OH, it will give you a very different reaction, and its behavior will be different from the entire chain. So the chemical properties are defined by the functional groups, and hence functional groups are very significant to study in the carbon and its compounds chapter. Okay. Now, what are these different types of chemical of functional groups? We're going to look at a few of them today. Okay. So how we write those is, I'm going to draw the structure of the functional group. The second thing that we are going to do is name the functional group. The third thing that we will do is, we will see how we put them in the nomenclature, as in how the nomenclature through these functional groups happens. And in the fourth, if there is any other remark or comment, we'll look at that, what is special about it basically. And right now, let's go one by one. So if we have a functional group which is a carbon with an OH, okay, so look, I'm not drawing a bond here, to just signify that O and H together is called as a functional group. So this is called as an alcoholic group. Okay, so it's just an alcohol. Now, how do we name this? So let's say I have a methane, right, which is CH4. Okay, when a CH4 gets to a CH3OH, we end up adding an OL to it. Okay, so this becomes methanol, right? So this is called as an alcoholic group. It's from the family of alcohols. And whenever we have an alcohol in the group, we just change the methane by a suffix. This is called as a suffix. Okay. So the suffix is added as ol. So it was methane. Methane has now gone to methanol, right? Now, and so on and so forth. The next functional group that we need to study is where we have a carbon double bond O and OH. This is sometimes also written as CHO. This is written as COH. There is a difference. Okay. CHO means that the oxygen is doubly bonded to carbon and one hydrogen. COH means that the OH group is bonded to carbon. Okay. This group is called as an aldehyde group. Aldehyde group. Okay. And here the suffix of L is added. Al. Okay. So when you have methane, this is methanol. Okay. Methanol. Quickly checking if others are able to see, and is if the YouTube is working well. Uh, okay. Everything looks good so far. Let me check if the YouTube is working pretty well. And is if the YouTube is working well. Excellent. Okay. Far. Let me check if the YouTube is working pretty well. Perfect. Yeah. So this is al. Okay, so aldehyde is always written with an al. The next group that we have is what we call as ketonic group, where instead of hydrogen there are all CH3 or other carbon atoms. Okay, so it could be. So I'm just going to draw a stick here so that you recall, that this is not an hydrogen. So there is just a carbon and oxygen, but no hydrogen in it. So you have any other uh, nomenclature on both the ends, or any other compound in both the ends, which is only of hydrocarbon. So only carbon and hydrogen will be here. Only carbon and hydrogen will be here. This group is called as a ketone. Okay, and its ending is with an one. Okay, so any compound you get like this will be, for example, this can be a methanone. Sorry, methanone cannot be there because since methane is the first compound, it needs at least three carbons. So one carbon should be on this end, and the second carbon can be on the other end. So the first possible is propanone. Propanone. Okay, so this is the ketonic group. The next that comes in the series is carboxylic group. This is a COOH. So this is the name. The family of this is called as the carboxylic groups, carboxylic acid or carboxylic group, and it ends with an oic acid. Oic acid. Okay. So for example, you will write this as propanoic acid. Propanoic acid. Getting it? So for example, yeah, so propanic acid, there is also methanoic acid. So you can also write this as methanoic acid. So these are all different foreign compounds, and these are the families of those compounds. And this is how, if we have to identify this compound in the mechanism, this is how we name it. Okay. Uh, for the time being, this is what we need to understand. I'm going to revisit this in a few minutes from now, but I'm going to talk a few points on nomenclature now. Now you see, if we really look at the series of alkanes, alkenes, and alkynes, the first one. So let's say these are the number of carbon atoms. Okay, number of carbon atoms. The first with only one carbon atom is CH4. This is an alkane. Let's talk about alkane, alkene, okay, and alkyne. Okay. So if you have only one carbon atom, this is an alkane. Now alkene cannot be there with one carbon atom. It needs minimum two carbon atoms. So this will be CH3, CH3. So here there would be two, okay, because there would be two bonds between the carbon atoms, and alkyne will be CH and C, only two hydrogens on both the sides. This first carbon atom is called as meth. It's always written with meth, and since it's an alkane, it is a methane. The second one here, it is meth, but since it's an alkene, it is methane. Sorry, not. So this first cannot be there. Here there are two carbon atoms, so I will have to directly go to ethene. Okay, since here also there are two carbon atoms, I will have to go to ethyne. Okay, so first one carbon atom is methane, two carbon atoms is eth, three carbon atom is prop, four is bute. You have known all of this, right? Five is pent, six is hex, seventh is hept, eight is oct, nine is non, and 10 is dec. Okay, so this becomes ethane, methane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Similarly, if I go to alkenes, except for methane, because methane cannot be possible, you need minimum two carbon atoms to have a double bond. So it becomes ethene, propene, butene, pentene, hexene, heptene, octane, nonene, decene. And alkynes also you need minimum two carbon atoms. So you cannot have a methine. You only end up from getting to ethyne. So it becomes ethyne, propyne, butane, pentyne, hexyne, heptyne, octyne, nonine, and decyne. Okay. So this is the nomenclature of all the carbon atoms. This is the sequence with which the names happen. Right. Now between alkane, alkene, and alkyne, it is very easy that you simply change A into E into ine. Okay. This changing of nomenclature is also possible with functional groups. So with functional groups, what happens? You change instead of methane, now you are saying methanol. So propanol, methane. Then you can also end up saying decanol. Okay, so all that. So this ending changes from all, L, on, and oic acid. Okay. Now, once we have understood this, let's try a few examples to see this in a much more depth. Okay. So let's say I have a straight stick chain compound, and I have a OH here. Okay. Now this becomes 1, 2, 3, 4, 5, 6. Okay, so there are six carbon atoms. So this definitely becomes hex. And since it is an alcohol, so I have to have a prefix ol. So it becomes hexanol. If I would have written hexane, then I cannot write this OH. If I've written hexene, then I will have to put a double bond. Hexine, I will have to put a triple bond, right? So this is an hexanol. Okay, so that is one nomenclature. Now let's look at one more. Let's say carboxylic acid. So this is the compound that I have, but here I have a O and OH. You remember that we do not generally write carbon, so I'm just writing double O and OH here. So how many carbon atoms are there here? 1, 2, 3, 4, 5. So this becomes pent, and since this is a carboxylic group, we'll use a suffix as pentanoic acid. Pentanoic acid, right? Because we know that if it is a carboxylic acid, the suffixes that we use is oic acid. Okay, oic acid. Now, so this is one way of nomenclature. Now, there is something we are so this is so what we have understood so far. Before I go to the next topic, just to be doubly sure, is that we know what are a few functional groups. We have seen four. We're going to see three more in some time, but the functional groups that we have seen are alcohol, aldehyde, ketone, and carboxylic acid. The difference between aldehyde and ketone is that the hydrogen that is there on the carbon on one side is replaced by a hydrocarbon. Okay, so there is no more just hydrogen, it is an hydrocarbon. So one example of ketone is this propanone is nothing but CH3, C double bond, CH3. But if I had to draw a propane with an aldehyde, it would have been something like this. So this is a propanone, okay. But let's say I had to write propanol, so it would have been CH2, C double bond OH. So this would have been propanol, okay. Now please understand why this double bond has come here, because on the carbon atom I need to have hydrogen only on one side. I cannot have double bond O and another alkyl group. If I have another alkyl group, this is called as an alkyl group. Alkyl group means anything that is derived from alkanes. So if there is an alkane group on both the C double bond O, then it is a ketone. But if there is a hydrogen, hydrogen is a must here. If there is a hydrogen on at least one end of C double bond O, that is called as a aldehyde and propanol. Therefore, you'll realize that here you have only one end that is free. So this will always be what we call as a terminal carbon atom. What do you mean by terminal? It means at the end of a chain. Now a chain can have a lot many threads, but at any one end of the thread you can have an aldehyde group. This is also always a terminal carbon atom, carboxylic group, because see it has only one free end. But for ketone, it has two free ends. I can attach any carbon atoms on both the ends. You know, I can attach. So, for example, here I have attached 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon atoms here. Here I have attached 1, 2, 3, 4, 5, 6, 7 carbon atoms, right? So this is a hydrocarbon. This is a nine-membered hydrocarbon, and they are on the opposite sides of the ketone. So ketone cannot be a terminal carbon atom. Alcohol also not necessary to be a terminal carbon atom, because alcohol can be at any central carbon, and on all the three sides there can be a there can be another hydrocarbons that are present. Okay, so this is the what you can say nomenclature as well as understanding of a few aldehyde groups. Let's do some examples, okay, especially examples that are there in your text to begin with. Yeah, now let's say we have to define a few compounds, or define rather name a few compounds. So what would be the nomenclature? So I'm going to give you a few compounds and see if you are able to predict the names. Okay, so okay, just 1 second. Yeah, so let's say I am drawing a compound for you. You have a compound which is like this. Okay, so let's say you have carbon, 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 and you have a double bond O, H. Okay, so this will be CH3, CH2, 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 and COOH. What do you think would be the answer for this? What compound could this be? Anyone? Yes. Okay. Let me check if you are able to respond anywhere. Okay. Yes. Are there any answers on YouTube or? Hmm. Okay. Any answers? What could this compound be? CH3, CH2, 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 COH. Where is everyone? Are you guys around? Mm-hmm. Yes, I think I can hear Ritu's voice a bit. Y- Yeah, but with pent, what would this be? So this is an aldehyde group. So what would be the suffix? So for aldehyde groups, what is the suffix? Al, right? Al, right? So like we are methanol, this would be pentanol. Okay. So this is just pentanol. Getting it? Easy? Yeah. Uh, okay. Now I'm still not convinced whether if everyone is there on the call and if I'm able to connect, because this is I'm having it's like a blind game that I'm having. I'm not sure if people are able to really watch and see, and therefore I'm concerned a bit. There are 7 viewers that I can see on YouTube now. Okay, Pentanal. Yes, I could see that someone could answer. Yeah, Shraddha could answer that as Pentanal. That's good, Shraddha. So I think a few are at least able to connect. Perfect. Let's go ahead. Dhruti, Anirudh, are you guys there? Can you just make your presence felt, because I don't know whether you're there or not. Wherever, either. Yeah, Anchita is here. Okay, excellent. Anirudh, are you there on the Skype? Anchita, that's good. I can see you. I can hear you now. Yeah, better. Perfect. Good, Anirudh. So keep interacting, because that makes me understand that we are. You guys are able to understand me. Okay. Right. So this is pentanol. I'm going to give you one more example, which is CH3. Let's say CH2, 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 and C. Uh, Let me put this as double bond O and CH3. Yeah. What could this be? Any guesses from anyone? Mm-hmm. Yes, Ritu, Anirudh, Anchita, anyone on YouTube? Yeah. What could this be? Mm-hmm. Guys? Mm-hmm. You're right in recognizing that it is a hex derivative, but this is not an all. Okay, so this is hexanone. Why? Because it is a ketone, isn't it? It's a C double bond O. So hexane is right. The suffix would be on. So it is a ketone, hexanone. Okay. Now we'll do some more practice maybe in the physical class on all of these. But just remember these. What I want you to remember is the sequence of all these: meth, eth, prop, but, pent, hex, hept, oct, non, dec, and and okay, yeah, this one of that. And what next you need to really understand is these alcohols, all one and oic acid. Okay, all of these work. Okay, now let's go and understand a few more about nomenclature, starting in alkanes, so the next level of complexity. Okay, now we all know that so far we have only seen straight chain compounds, which means that if you have C and C, this is a straight chain compound. What happens if you have a compound that is on the top? Okay, CH3. How do I name this, right? Because this compound is very different from having 5 carbon atoms like this. Okay, C. Okay, so here we have CH3, CH2, 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 CH3. So these are 5 carbon atoms. These are also 5. The only difference is this carbon atom, the end one, is now at the top. If you really see, the formula for this is C5H 12 H12. Yes, 3 plus 3 6 plus 3 9, 9 plus 3, that's 12. This is 3 plus 3 6, 6 plus 6 is 12. Here also the chemical formula is C5H12. But the difference between them is their structure. Okay. So if someone tells me tomorrow, let's say Dhruti comes up and says, "Sir, I'm studying about C5H12." I will not be really understanding whether she's studying about this compound or this compound, or I will tell you there is one more compound that can be formed, which is like this. Okay, CH3, 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 CH3. The formula for this compound is also C5H12. Now, out of these 3 compounds, which one is she really studying? I have no idea. So, hence, all of these 3 compounds have the same chemical formula but different structural formula. So the structural formula is different, Okay, different, but it has the same chemical formula. Okay, now when you have this kind of a situation, all of these together, same chemical formula or molecular formula, right? Molecular chemical formula. When you have this kind of a structure, all of these three together are called as isomers. Isomers. So what are isomers? Isomers have the same molecular formula, but they have the different structural formulas. So all are C5H12, but their arrangement is very different. So they are called as isomers. Now isomers can be because of different ways. This is just one way of writing an isomer. In fact, if I have to tell you, this is also an isomer. For example, check this. Okay, now I'm writing a compound CH3, CH2, CH2OH. Okay, the formula for this is C3H. If you see 3 plus 3, 6 plus 2, 8, this is H8O. This is the molecular formula for them. So general molecular formula I'm talking about. But if you really see, if I write like this, CH2, CH, CH3, OH. This is also C3H8O, but these two are completely different compounds. For example, this compound very easily does not react very easily, but this compound reacts very easily with bases. Their properties are very different, their densities are different, all of that is different. So if that is the scenario, how do I identify these? These are again isomers. Now I'm going to draw one more compound just for your understanding. I am drawing CH3, CH2, C double bond OH. Okay. Now the formula for this compound is C3H6O. Okay. Now I'm going to draw a compound which is like this: C3, C double bond O, CH3. This is C3H6O again. Now this actually is an aldehyde. If you see, this compound is CHO group. So here if you see, this functional group itself is CHO. Okay. Whereas this functional group is actually CO. Okay, this is a CO functional group. Now if this is the difference between both of them, then the formula remaining the same, the functional group itself has changed. So these are something called as functional isomers. Okay, functional isomers. These are called as position isomers. So isomers that are happening through, excuse me, sorry, this is isomers happening through position. This is isomers happening through change in the functional group itself. And in the previous scenario, I'm sorry, in the previous scenario we are having functional groups which are there is no change in anything except the chain has changed. This is a straight chain, this is a branched, this is highly branched. Okay, so these are different chain isomerisms. So isomerism happens through different ways. Okay, but whatever the reason is, having a different structure, being a different molecule, but having the same chemical formula is what an isomer is. Okay, now let's look at a few more isomers in such terms. Okay, now if I have a carbon compound like this, okay, CH3, okay, and then I have a carbon compound which is CCH3, CH3, CH3. So I've taken a very unique molecule just to show you a point. This carbon is attached to only one carbon. Okay, since it is attached to only one carbon, it is called as a 1-degree carbon compound. This carbon atom is attached to two carbons. So it is one on this side and one on this side. So any carbon atom which is attached to two carbons is called as a 2-degree carbon atom. This carbon atom is attached to three. It has 1 year, 1 year, and 1 year, but rest are all hydrogens. So this is a 3-degree carbon atom. And this is attached to four. 1, 2, 3, 4. So this is a 4-degree carbon atom. Okay. So what are the different degrees of carbon atom? Any carbon atom who is attached to one carbon atom is called as a 1-degree carbon atom or a primary carbon atom. Any carbon atom that is attached to two carbon atoms is called as a 2-degree or secondary carbon atom. Anyone who's attached to three is 3-degree or tertiary. Okay. Can you tell me what is this carbon atom? Is it primary, secondary, or tertiary? Yes, anyone? What carbon atom is this? Mm-hmm. Any answers, guys? You there?
Primary.
Yeah, that's primary. Correct. Okay. Yes. So this is a primary carbon atom. Why? Because although this is tertiary, this carbon atom is only attached to one. So it is primary. This carbon atom is to attach to four carbon atoms in all of its vicinity. This is quaternary. For four carbon atom is also called as quaternary carbon atom. Okay. But you see all the others, these are primary carbon atoms. Sorry, 1 degree primary carbon atoms. Okay, all are 1 degree carbon atoms. Now, okay, so now that you know this, what are primary, secondary, and tertiary, there are some different names also for this. So generally, a carbon atom which has a single carbon atom coming out is called as an isocarbon atom, and this is called as a neocarbon atom. Okay, so for example, if you have a CH3, CH2, CH3, this is an N-propane. This is N-propane. N-propane means normal propane. Okay. When you have a carbon atom which is coming out at the top, okay. So for example, you can have CH3, CH, CH3, and a CH3. This is an isobutane. Isobutane. Okay. Why butane? Because now there are four carbon atoms. Okay. So this is an isobutane. Now, if you have five carbon atoms coming out, okay, this is a CH3, CH3, CH3. Now there are five carbon atoms. This is a neopentane, neopentane. But having said this, these are very unique names, guys. So these are only used in common nomenclature. In IUPAC nomenclature, this is not even a pentane. This is a propane. In IUPAC, this is also a propane. But in common nomenclature, this is a butane, because in common nomenclature, you take the total number of carbon atoms. In common nomenclature, here also you're taking total number of carbon atoms, which is five. In common nomenclature, you're taking total number of carbon atoms, which is four. Okay, here there is three. Okay, so all that really matters. Okay, now so these are structures, isomers. So what are the total concepts that we have seen today? I just don't want to rush because of it. This online classes gives a lot of flexibility to move through the topics, but I want you to be with me. So what are the things that we have seen today? Today we started with functional groups. In functional groups we said, okay, these functional groups can be different foreign atoms or molecules that can be joined to the main carbon atom, and they dictate the chemical properties of the carbon atom. That's very important. Then we said, okay, what are these functional groups like? So then we found that this is a COH or only OH. Okay, here there is a CHO. Okay, so there is a CHO group. Then we found that ketones, there are only CO, but on all the both the sides there are alkyl groups. So in ketone, so alcohol is also called as OH group. Aldehyde is also called as CHO group. Ketone is called as CO group. Okay, and also represented something like this, sometimes like this, and this is called as a COH group. So represented sometimes like this. Okay, so remember how they are represented also. Aldehydes are represented as CHO or C. If bonded form, it is written like this. In short form, condensed form, it is written like this. Ketone is written only like CO, like carbon monoxide is written, because there is only one double bond between carbon and oxygen, right? And carboxylic acid is written as COOH. Okay. In nomenclature, you have ol, al, one, and oic acid. Okay, on al. So this is the nomenclature. You end it writing as propanol, propanal, propanone, propanoic acid. Okay, non al, all of this. This is what we saw. Next thing we saw this series of the entire structure one by one. I'm going to send you these notes, so don't bother, But I would also like you to take your own notes, maybe writing of those. I'm going to send this PDF to you any which ways on the group. But having said that, it's good to keep on taking your own notes as well. Okay. Now, if you really see that we have seen a few examples. So, for example, this is an hexanol, this is a pentanoic acid. And all of these examples, please note that we have attached the functional group only to the end. That does not mean that it should be attached only to the end. You can attach it anywhere. So, for example, here also we have attached it to the end, attach it to the end. But this is just for the simplicity, right? And we have taken straight chain compounds. Here we have started taking branch chain compounds. So here we saw the concept of what are isomers. Okay, isomers are different compounds with the same chemical formula but different molecular structure. And then in the end, we also saw that, okay, now I'm changing the functional group to the center also. So I'm changing the position. Sometimes I'm changing the functional group, the formula remains same, and yet the compound molecule completely changes. Okay. And then we saw what are primary, secondary, tertiary, and quaternary. functional groups. Now what we are going to see is what are homologous series. Homologous series. Homologous series are all those group of compounds, carbon compounds, which have same general formula. Okay. Remember, isomers had same molecular formula or chemical formula. Here we are talking about the general formula. What is the difference between general formula and molecular formula? General formula is like an equation, like a code. Okay. For example, CnH2n plus 2. This is like a code. I can put any value of n. I can put n equal to 1, 2, 3, and any of that, right? If I can put n equal to 100 also, does not matter. Now, if I put n equal to 2, for example, I get C2H6. Okay. If I put n equal to 3, I get C3H3 to the 6 plus 2, 8. Okay. Now, if I expand this, this molecule looks like this: CH3, CH3. This molecule looks like CH3, CH2, CH3. Let's take one more: C4H10. This molecule looks like CH3, CH2, CH2, CH3. If you find, incidentally, I am getting all similar kind of compounds only. Okay, so all of these are alkanes. Now, someone might come up and say, sir, I can write C4H10 like this also: CH3, CH, CH3, CH3. And this formula is also C4H10. But this I cannot include. Okay, so I will not include this compound because it has changed the way that I'm writing. Here I was writing all straight, now I started branching, so this cannot be used. Okay, but for all of these circumstances, the pattern remains the same. So what are homologous series? They have the same general formula, but incremental molecular formulas. Molecular formulas. Okay, molecular formulae. Okay, now, okay, so if someone asks me, what is the importance of this? You see, all of these turn out to be normal alkanes, N alkanes. Okay, N alkane. Now, why I am saying normal? Because they are all straight chain. So now you understand what is normal and what are branched or iso and neo carbon atoms. So what are normal alkanes? Normal alkanes are all straight chain compounds. And I can write even C100. For example, C100 would look like C100 plus H202. Okay, by this formula. So that is also an alkene, and therefore all of them are homologous series. So this is an homologous series. All are the members. So each of these is a member of homologous series, and this is a series. Why do we not call it as homologous group? Why we are calling it as homologous series? It's because it is actually like one after the other, like 1, 2, 3, 4. So there I will always find a member which is uniquely placed equidistant from the previous member. Okay, uniquely placed equidistant from the previous member, which means for C3H8 I will find C3H8 only. I cannot get C3H7 or C3H9. I will get C2H6 only. I cannot have C2.5 and H something. That's a nonsense way of saying things, right? So equal distribution. Another way to look at it is, if you really look at their difference, what is the difference between these two? It is CH2. What is the difference between these two? It is CH2. What is the difference between, let's say, C4H10 and C5H12? It will again be CH2. Okay, so the each member of homologous series is is always differentiated by a CH2 group. Okay, now, acha, why are we studying this? What is the importance of studying homologous series? If anyone has to ask anything, you can please go ahead and ask her, because I think someone, yeah, if someone has to ask, just feel free to ask up. Yeah, Anirudh, you were saying something? You
No, sir.
okay? Yeah, you got unmuted.
By mistake, my bad.
Okay, okay, no problem. Yeah. So all of them are with a difference of CH2. Now, you see, why are we studying homologous series? Now, in a homologous series, the properties, the chemical properties of all the substances are the same. Okay, slightly different, but majorly they are all the same. Okay. So, for example, how C2H6 will react with, for example, a base, everyone will react with the base similarly. Okay, with slight variation. And one more important point is, so similar, I would say, chemical properties similar chemical properties. See, I have not said same chemical properties. Similar means very close to each other. And the next most important thing is incremental physical properties. Incremental physical properties. What does this mean? That if there is a density that I'm looking at, if the density of, for example, C2H6 is say 0.1 gram per liter, okay, because it's very small in volume, very light in volume. Then if this, so I'm just taking some random numbers, okay. So say this is zero point 0.2, then this will be zero point 0.3, this will be zero point 0.4, maximum this will be 0.48, my instead of zero point 0.5. So the increment is quite patterned, it's quite predictable. That's very important thing. So but they will incrementally rise, okay. So their weight, of course, if you see the molecular weight, this is 24 plus 6, this is 30. The molecular weight here is 12 plus 2, 14, so this is 44. So this is the incremental weight here is 58, okay. Now the difference is all 14, 14, 14, because CH2 group is changing. So molecular weight are incrementally increasing by 14. So in homologous series, all the properties of chemical properties are more or less the same, and physical properties slightly keep on increasing one after the other. So what are the physical properties? It could be its weight, it could be its boiling point, it could be its melting point, it could be its density, it could be the state that they are in. So earlier would be gases, then there would be liquids, then there would be solids, and then there would be denser solids, so on and so forth, right? So physical properties incrementally increase, chemical properties remain the same, because they all being alkenes, no functional group or their functional group being just the same alkene that they are, their chemical properties remain the same. So that's homologous series. Now, what are different types of homologous series? So this is an alkane homologous series, but I can also have an alkene homologous series. Alkene homologous series will start with CH2, CH2. With ethene, I cannot start an alkene homologous series with methane. Okay. Now, what could be the other one? This is there, CH2, double bond CH2. What will be the next? CH3, CH2, CH2, double bond CH2. Sorry, this will be CH. This will be CH. Okay. Because yeah, and so on and so forth. I'm just going to draw one more. CH3, CH2, 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 double bond CH2. Okay. Now, so what is the formula here? It is C2H4. The formula here is C3H6. The formula here is C4H8. Check 2 plus 2 plus 2. Uh, oh, this is CH. Here it will be CH. This will be CH and CH. Okay. So this is 2 plus 1, 3, 3 plus 5, 8. Here it is 3 plus 2, 5, 5 plus 2, 7, 7 plus 3, 10. So this is C5H10. So for alkane, we had a formula which is very important. You should also remember this formula very well. So I'm going to box it. So the formula was CnH2n plus 2. Okay. Now with alkenes, suddenly, because I am always missing two hydrogens, my formula becomes CnH2n. Okay. So if you really put n equal to 1, n equal to 2, you will get C2H4. If you put n equal to 3, you will get C3H6. If you put n equal to 4, you are getting C4H8. So this is the general formula for alkenes homologous series. Okay, homologous series. Now similarly, you can also have for alkynes, and I'm just going to write directly here, it will become CnH2n minus 2. Now please note, whenever I'm saying this is the homologous series, I am talking about only one double bond. Everywhere there is only one double bond. If I start putting two double bonds, the general formula would change. Similarly for alkynes also, there is only one triple bond. There are not more than one triple bond. Okay. So quickly, once again, quick revision. After we saw that what are 1 degree, 2 degree, 3 degree, 4 degree carbons, and what could be the common nomenclatures for a few things. This is a neopentane. Okay, but remember in IUPAC this is not pentane, this is propane. You have to remember that. I am saying this again and again. This is an isobutane in common nomenclature, but in IUPAC nomenclature, which we will study in a few minutes, or maybe in the next class, this is actually propane. Why? Because longest chain is considered there. Now, homologous series is the series which has general formula same and increasing physical properties but similar chemical properties. General formula for alkene is CnH2n plus 2. For alkene, it is CnH2n and CnH2n minus 2. If you really observe, if I write all of them in the same, okay, 2n plus 2, one below the other, if you see, you will realize that the difference between them is two hydrogens. Okay, so this is the difference is two hydrogens, and difference here is also two hydrogens. Why? Where does those two hydrogens go? Those two hydrogens go when this bonding happens. So CH3 was there, two hydrogens I take out, that single bond has, that single bond has now become double. So I remove two hydrogens, I end up getting alkene. I remove another two hydrogens, I will end up getting alkyne. So for example, the first alkyne would be simply CH triple bond CH. Please note CH triple bond CH and this are no different compounds. They are the same compounds. Okay, I'm just writing hydrogen at the back and the fourth, and then the fun. Whereas this is a much better way to write it. Okay, so what has happened is I have just made single bond into a triple bond, and I've taken out two more hydrogen atoms. Okay, so that's alkynes. Hmm? So good. So what we have seen today are different types of compounds nomenclatures. There's one more very important point that I'm just going to share is what are alkyl, alkynyl, and alkynyl groups. Okay, so let's say I have CH4. Okay, now instead of this CH4, I want to attach this group to a larger compound. Let's say this compound. Okay, so this was another compound, but I want this CH4 to attach it. So how will I attach? I'll have to remove one hydrogen and then attach. So I will attach it like this. Okay. Now, since this was created from a methane and it was joined here, this is called as a methyl group. Okay. So methane becomes methyl. Okay, similarly, see, if I would have joined here as CH2 CH3, now this actually would come from CH3 CH3, so this is ethane, and it will turn out to be an ethyl group. Okay, so from ethane it's going to turn to ethyl. Okay, now let's join one more. Okay, let's see if I can join CH2 double bond CH2. Okay, so I'm using the same compound so that you realize the difference. Now here I'm going to again take out a hydrogen and this will be joined here, so this will be CH double bond CH2. Now since this was ethene and ethene came to join here, this group is called as ethenyl group. So check, this was ethyl, this is ethenyl. Ethenyl, very simple. Ethene becomes ethenyl. Here ethane becomes ethyl. And let's say here if I join C triple bond CH, this will be ethenyl. As simple as that. So ethene becomes ethenyl, ethyl becomes, so this comes from ethine, which is CH triple bond CH. This is an ethine. So ethine becomes ethinyl. Ethane becomes ethyl, and ethinyl becomes ethene becomes ethinyl. Okay. So this is one more very important point that we need to understand. We also know now the general formula of all the hydrocarbons, whether it is straight chain, branched, or alkyl or alkene or alkynes. Okay. So now, okay, I just want to pause here for a minute. Can you guys quickly come back saying, are you getting this? Is everyone with me? Okay, good. So I'm seeing there were some comments here. Primary, sir, screen not clear. Okay. Higzain, Anchita, perfect. Ritu says yes. Anirudh is also okay. Brilliant. I think everyone is there now. Okay. Um, Okay. So now the guys who are on YouTube, you are going to have slight lag, and therefore whatever I paused for, by the time you respond, I would already be doing something else. So, but that's okay. You can always put a comment, and I can always see that to get back to you. So that's not an issue. Okay. So let's go back to our understanding of the chapter further. Now, so how do we name alkenes? Okay, so this is another very important point. How do we really name them? Now, in naming, you have to remember these three things. Okay, what are the three things that you have to remember? The first is you have to find how long the chain is. Okay, what do you mean by how long? So let's say I have this molecule CH3, CH2, CH2, CH3. Okay, so this is a three-step long chain. So this is called as a propane. Okay, propane. Okay, now if it is three, if I put a double bond, okay, if I put a double bond, it becomes propene. I'm going to take a slightly longer chain for you to realize the difference. So let's say I take CH2, 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 CH3. So how many carbon atoms are there here? Now it starts from here, it becomes 1, 2, 3, 4, 5, 6. Since there are 6 carbon atoms, this becomes an hexane. Okay. Now what I'm going to do is I'm going to erase one of them, two hydrogens, and I'm going to create a hexene here. Okay, so this becomes CH double bond CH2. So this becomes hexene. But tell me, how is this compound different from CH3, CH2, 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 CH, sorry, double bond CH, single bond CH3? Or how is it really different from CH3, CH2, CH, double bond CH, CH2, CH3? All of them have the same formula, which is C6H12. Okay, so check everywhere, you will find 12H. 1, 2, 3, 4, 5, 6. Yeah, this is 6. So this is 3 hydrogens. 3 and 6 are 9, 9 and 3 are 12. Here also you'll find 12. So everyone has C6H12. In fact, everyone has a double bond, but the double bonds are placed very differently. Now, how do we handle this situation to differentiate these compounds? Is we number these compounds with different, what should you say, numberings. Okay, so for example, in the first scenario, the carbon atom is central. So wherever we go, we start numbering them. Okay, so let's number them. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Okay, now why did I start from here? I could have also started from here, from the other end, but you should start numbering from there where the smallest number can be given to the alkene. Okay, so if I start from here the smallest number given to the alkene is 1, therefore I write this as 1 hexene. Here I write 1, 2, 3, 4, 5, 6. The smallest number can be given to 2, so this becomes 2 hexene. Okay, here I start from here, 1, 2, 3, 4, 5, 6. The smallest number can be given at the third carbon, so this is 3 hexene. Okay, now I'm going to show you a variation, and this is something that is very interesting, is that see, CH3, CH2, here I put a double bond. Okay, this time, so I'm going to put a double bond here and make this as CH, and I make this as CH2, CH2, CH3. Now, if you guys come up and say, look, sir, you started numbering from here, let's number from here only. Okay, so let's number this as 1, 2, 3, 4, 5, 6. This will be wrong. Okay, why? Because we decided that the lowest number should be given to the double bond from that end wherever it is possible. So here this numbering will not work. This numbering will work. 1, 2, 3, 4, 5, 6, and therefore this molecule also is 2 hexene. It is simply a mirror image of this. So if you take this molecule, like a strip of this molecule, and you simply reverse it, like you turn it like this. Okay, you'll end up getting this compound. Okay, so if you end up getting that compound, you basically find that the both the hexenes remain the same. Okay, give me 1 second, guys. I think yeah, just 1 second. Yes, so where is, okay, so right, so now, oh, I hope there's no questions yet. Okay, perfect. Yeah. So how did we really distinguish this is that, so for hexene, there are only 3 straight chain isomers, we will say, because see, the molecular structure is very different. Sorry. The molecular structure is very different. These 3 are 3 different compounds. Minded guys, for looking at it, everyone would say, sir, what, this is alkene only. There is a double bond here. There are also double bonds here. So what? It looks very much the same. But no, that they are not the same. The way that this compound reacts with compounds, like I have given you some examples. So, for example, if I put Ki in this compound and I put Ki in the other 2 compounds, I'm going to get different products. I'll not get the same product. Okay. So therefore, these 3 compounds, they look similar, but they are very different, because the difference is the change in the molecular positions. So all those people who have given NTSCs or who have studied MAT or something, in that we used to find out find the odd man out, or which figure fits best, or can you find the mirror image. So these organic compounds are very similar to that. All of them would have different mirror images, different ways of really changing structures, maybe water image. So if you really see, these two are actually mirror images of each other. So if I put a mirror in front of this, okay, if I put a mirror here like this, you'll find that this compound is exactly the mirror image of this, nothing else. Okay, so they are not very different compounds. So unless you are able to figure out a completely new compound which cannot be overlapped or in any way matched with the earlier compound, you have to give it a different name. And because it's a different compound, right? So you have to have a different name. Maybe they are like twins or triplets or quadruplets, something of that sort. So if you have that kind of a scenario, you'll have to have a nomenclature system which can recognize that. So here we are able to recognize that with different numbers. Okay, so numbering is what, this is a new term that we have just seen. Numbering is very important. Okay, so that's how double bonds are numbered, and that's similarly triple bonds also. So it becomes one hexane, two hexane, three hexane, so and so forth. Okay, now so, now that we have understood this, we are also going to see how we are going to number different compounds. And let's take our butane, right? We have been talking about it, and I said I'll show you that in a few minutes. So let's say you have CH3, CH2, CH3, and CH3. We saw a few minutes ago that this is called as isobutane. Okay, but in IUPAC nomenclature, so this numbering and chain, all of this formula is called as IUPAC nomenclature or IUPAC nomenclature. Why was the nomenclature established? So they established a rule that if we name the compounds in this fashion, so you see in computer science, you know how we name the folders and files. We name it in a certain fashion so that we remember, where the file was kept and what file it is. If we do not number it with the same file number, then we will be confused. Array, which file was where, and how to really communicate to other people that okay, this the file is kept here or something like that. So path is there, number is there. Similarly, IPSC was established to give this numbering in a very different, in a very typical fashion, nothing else, right? So we can uniquely have a compound. Now, in this scenario, isobutane is what the molecule really looks like. But if you really see, there are three carbon atoms. So what is the first rule? The first rule is find the longest chain. And what was the second rule? The second rule is that number the chain such that you get number the chain such that you get smallest number to the number the chain so that you get smallest number either to the double bond first, to double bond, or if there is no double bond, then to the substituent. Okay, what does the substituent mean? Substituent means on this longer chain, what is the branch that you have? So substituent means branch. Okay, so what is the substituent here? Here the substituent is this CH3. So what do you mean by, so what substituent is this? I told you that this substituent is derived from methane. So this substituent is called as methyl. Okay, and which is the longest chain? This is the longest chain. Okay, does that mean that this is not a longest chain? Yes, it is also a longest chain. You can take that also, no problem, no problem. If there is a conflict in the longest chain, take that longest chain. So see, if there are two long chains, why am I saying this is also a longest chain? Because this is also three-membered carbon ring. So longest chain does not mean that the molecule has to be straight. See, this is just the writing, the representation. The molecule does not look like this. The molecule in fact looks very differently. I've shown you. So let me also show you here today, how this CH3 molecule will really look like. So if I have MOL view, it's how the molecule really looks like. The molecule looks like this. Okay, let me clear this first. Okay, now I'm going to take a carbon. So what is this? This is a CH3, CH2, CH3, CH2. So isobutane. Let me just figure it out. I'll have isobutane. Yeah. Okay, so see, the molecule actually looks like this. Okay, so you see this is one CS3. If the way that I've written on the notebook, if I have to write it that way, let me just align it that way. Okay, yeah. Now see, this is how I've written it: CS3, CS2, CS3, CS3. But in 3D space, this is CS3, CH2. Are you able to, oh, why am I written CH2? This is CH, sorry. Yeah, CH, then you will find CS3. So look, there are three hydrogens here. There are three hydrogens here. There is a carbon, there is a carbon, there is carbon and one hydrogen, and there is carbon and another 3 hydrogen here. So this is the same molecule, but that does not mean that the molecule actually is straight chain. So if I ask you which is the longest chain, this is also a longest chain, this is also a longest chain, this is also a longest chain. All three of them are longer chains, and none of these chain is different from anything else. So it does not matter which chain you take. I will change you. I will tell you the difference in longest chains in another example. So for example, look, if I take a molecule like this, okay, then this longer chain, and okay, let me take it uh, this way. Okay, so uh, one, two, three. Okay, now look, this is a chain that is 1, 2, 3, 4, 5, but this chain is 1, 2, 3, 4, 5, 6, 7. This is 1, 2, 3, 4, 5, 6. So the chain that I will follow is this, because this is the longest chain. It is actually having 7 members. This is having only 6, and this is having only 4. This is having also about 6. So this is the longest chain that I take. Longest chain you take, and then you start numbering. So where will I number from? I number in such a way that this substitute gets the lowest number. So this is 1, 2, 3. So even if I start from here, it will still give me this as 2. So what will the name of this compound be? This compound is named as 2. What is the group at 2 position? What group is there? Methyl. 2 methyl but no, not butane. There is 3 membered ring, so it is propane. Okay, so I told you that butane becomes propane in IUPAC. Why propane? Because in the longest chain there are 3 carbon atoms. So the longest chain gives you what we call as the root. Okay, and this root has come here as propane. Okay, so the longest chain gives the root, and root gives it as propane. Now at the second position you are having a methyl group, and therefore it is 2 methyl propane. Okay, because the substituent is methyl, right? So that's how we number the chains. Okay, and we have nomenclature done. Now let's look at neopentane. uh, the second chain, we let's look at the this molecule. Yeah. Okay, so now here also the longest chain are any of these. So I'm going to draw all a few lines for you. This is also a 3-member ring, this is also a 3-member ring, this is a 3-member, this is a 3-member, this is a 3-member, this is a 3-member. All of these chains are 3-membered. So we take any of those. So last time we took straight, this time we will take something different. Okay, so I'm drawing the same molecule. I'm going to take this as a chain because all of them are same, there is no difference. I'm going to take this as the longer chain. Okay, since it is a 3-membered, the first thing that I write it as propane. Now on this propane I have to do the numbering is my second rule. So I can start numbering from here: 1, 2, 3. Now since there are at the second position, at the second carbon, there are two groups, two substituent groups, these and this. These are the branches on this chain. Okay, so what do I write them as? Now since both of them are there, I have to write positions for both. So I write this as 2, 2, because at both the positions there are 2, 2. And what groups are these? Both are methyl, so I write this as dimethyl. Please note, I cannot just write 1, 2, because for every group I have to write a number. So I write this as 2, 2 dimethyl propane. Okay, so I am not going to go to much more complex numbers here, but I'm just going to revise nomenclature one more time. What are the rules? The rules are: you take the longest chain. The longest chain, you do not calculate total number of carbon atoms in the molecule, you calculate total number of carbon atoms in the chain. So if you take the longest chain, there are 3 carbon atoms. So you say this as propane. And then in this 3 carbon atoms, you number the number of atoms on the carbon atom. So 1, 2, 3, so on and so forth. At whatever number you are getting a substitute, you write that number. And this number should be lowest. So your choice of numbering should be such that you get the lowest number on the substituent. And whatever is the group that you write after that number, and you say 2 methyl propane. Okay, so that's nomenclature, IUPAC nomenclature for us. In alkene, that numbering will be for double bond or triple bond. And alkyne, it will be for triple bond, right? Yeah, similarly here. So I'm just going to pause here for a minute and ask you guys a question, and then we will move to probably we'll have the last session for today. So can you guys name this? Yeah, try and name this compound. Try and name this compound. It's an easy one. See if how many of you are able to do that. Yeah. Let's see how many of you are able to really do this. Yeah, numbering part. How did hexane become 2-hexene? Anchita, did you get the numbering part? If not, you can please comment on the YouTube channel once again. Yeah, Anchita, if you've not got that, you can comment on the YouTube channel one more time. Okay, you have got it. Seems good. Uh, See, numbering is simply the same. Yeah. So what you do is you start from any end of the carbon atom. So, for example, your whichever chain that you have chosen. Once the chain is chosen, you start numbering from one end. Okay. Once you have started numbering from that end, you do the numbering in such a fashion that the substituent should get the lowest number. That's it. So, for example, how did hexene become 2-hexene? Is because I started numbering from this side, and in this side, at the second carbon, there is a double bond, so it becomes 2-hexene. Okay. See, I could have also started from here. From if I would have started from here, it would have become 1, 2, 3, 4. So it would have become 4-hexene. But 4-hexene cannot exist in nature. There is no compound called as 4-hexene because the naming itself is wrong according to the rules. The naming should be in such a fashion that if there is a lower number possible, there is a lower number that I have to give. So 4-hexene cannot exist in nature. There cannot be 4-hexene. You can only do 2-hexene because 4-hexene is nothing but what you are trying to say. Basically, it was 2-hexene. I should have numbered other end. Okay. So that's how numbering has to be done. So what is the rule of numbering? The rule of numbering is start from any end of the carbon chain, but number in such a fashion that the numbering should be smallest to the functional group or to the substituent that you have. Simple as that. Okay. Anyone else who has, yeah. So what is the answer to this compound? Who can give me the nomenclature to the compound that I just mentioned?
Is it 2,3-dimethyl butane?
2,3-dimethyl butane. That's right. That's right. Now, guys, let's look at this, how this is. Okay. Now, just for your surprise and trick, I'm not going to choose this. So there can be multiple chains that are longest. See, this chain is also longest, which is of 4 carbon atoms. But I'm going to choose the blue one just so that to show you that it does not make a difference if the chains are the same. I'm going to choose blue. It also has 4 carbon atoms. Check 1, 2, 3, 4. So if I name through the blue one, it will be at the blue one. This is a substituent. Okay, and this is a substituent means branch on the main chain. Now if I start numbering, I can number from here, which is 1, 2, 3, 4, or I can number from this side. It also becomes 1, 2, 3, 4. So in either cases here, 2 and 3 is where I'm getting my substituent. So this becomes 2, at the substituent is at the second carbon. This is the substituent again at the third carbon, and both of them are methyl substituents. So I will write this as 2,3-dimethyl. And how many total number of carbon atoms are there in the root? 4. So therefore it will be butane. Okay. Now let me name it through the pink one. Let's see what turns out. For the pink one, this is my substituent and this is my substituent. Okay. So I can start from here 1, 2, 3, 4, or I can start from here 1, 2, 3, 4. In any which ways, I am getting 2 and 3 as my substituents, the red ones. Check the red ones now. So through the pink also, if I number, it becomes 2,3-dimethyl butane only, and therefore it is okay to number in any fashion. Okay, it gives me the same product. Okay, is everybody connected to this? Can you guys just quickly confirm all that you are there, whether you are on Skype or on YouTube? Either you say, or instead of saying, I think you can just comment in the Skype if possible, or on the YouTube if possible, so that I know that you guys are getting this. Yeah, Anchita, Shraddha. Yeah, can you please comment and just confirm, because we are just coming to the end of the class. I just want you to know that. I mean, okay, perfect. Yeah, okay. Ritu says got it. That's good. Uh, okay, perfect. Yeah, that's nice. Perfect. Good. So what I'm going to do, guys, is what I want you to do is, because we're just at the end of time and I have a next class to really get into, is that what we will do is I'm going to send you the perfect. What if the substituents are not the same? Then you just use the different names of the substituent. For example, you will say this as 2,3-methyl ethyl. Okay, methyl ethyl. And not just the substituents, there are a lot many conflicts that we are going to see, but I don't want to complicate at this very stage. I want you to really contemplate on this. There are multiple variations that we will see in the next class whenever we meet next. We'll also going to have a question paper discussion in the next class. So I'll be giving you your answer sheets and we'll have a discussion on that because that's been pending. But yes, if the substituents are different, then we simply use those substituents with the number. Okay, so we'll say this as at 2 there is a methyl, at 3 there is an ethyl, so and so forth. Okay, so we are going to see those variations also slightly in the next class. Okay, good. So fine, guys. This is what I want you to really do. And since this is already also in the recording, you guys would find that please go through your text. Your textbook also has some questions. What I'm also going to do is I'm going to send you a nomenclature sheet right now. Right away, I'm sending this uh, on the group. Okay, so please go through those nomenclature rules also once before coming to the class, because there is nomenclature is slightly tricky subject in terms that there are too many rules to really remember in the first go, but it only needs slight practice. So it's like chess, all the rules that if you remember, then you are able to play well. Similarly, in nomenclature, if all the rules are clear with you, then you'll be able to do it in a much better fashion. So let's do that. And next class, whenever we meet, we are going to discuss nomenclature in much more detail. I'm going to send you two sheets. One is that I'm going to send you the PDF of this itself, okay, the PDF of whatever we have done today. And the second is I'm going to send you the nomenclature rules PDF on the group. Please go through this PDF and try some examples that is there in the nomenclature also. Okay. Okay, good. Thanks for joining in. I hope we were able to connect, although we got a bit late in joining in. There's technical, problems you have to sort out before we join the class. So from next time, let's do it slightly earlier than where we begin. Okay. Take care, guys. Bye bye. Yeah, I'll see you in the class next time. Good. Take care. Bye.